Hello everyone, I'm Ritika Jaiswal. I'm a PhD researcher at the University of Stavanger, Norway. Today I'm going to talk about my paper titled A Simple Algorithm for Finding Steiner Spanning Trees, which I wrote along with my supervisor, Professor Reggie David Raju. Before talking about the algorithm, let's talk about graph algorithms, as graph algorithms are the basis for Steiner algorithms, Steiner trees. And so graph algorithms are inevitable in the modern world, and they're used in major ICT applications. Um, and spanning tree algorithms like Prim's and Kruskal algorithm, which are basic graph algorithms, are used in Google Maps and social media like Facebook, and also in network design. So they have various applications. In this paper, we present a simple algorithm for finding Steiner spanning trees. Now, what is a Steiner spanning tree? It's a tree which connects a set of terminal vertices. So in a tree, we have we have subset of vertices which are called terminal vertices, and there are non-terminal vertices. So we want to connect all the terminal vertices in the minimum total edge weight possible. And to connect all these terminal vertices, we need some of the non-terminal vertices. So this non-terminal vertices which provide help to us to connect all the terminal vertices are called Steiner vertices. And so it's the name called Steiner spanning trees. Now this algorithm which we propose, it uses modified Prim's algorithm to generate minimum weight spanning tree as the basis. And then the non-terminal weights vertices with 1 degree of connection is deleted until the resulting tree becomes free from any non-terminal vertices with 1 degree of connection. So this is the approach which we provide, because finding a Steiner spanning tree is a NP-hard problem. So our approach, it solves the problem in polynomial time. Now this algorithm is also easy to understand and is implemented in GPenSim software for industrial applications. Now, what is a minimum weight spanning tree? So as the name suggests, minimum weight. So there are set of vertices and there are set of edges, and we want to connect all these vertices such that all the weight is minimum to connect all these set of vertices. And in literature, we have two simple algorithms for finding solving the minimum spanning tree problem. So first is Kruskal algorithm and the second is Prim's algorithm. Both Kruskal and Prim's algorithm are greedy approach. They use greedy approach, and they do provide both of them globally optimal solution for the minimum spanning tree. Talking about the runtime, for dense graphs, Kruskal algorithm takes big O of v square log v time, whereas Prim's algorithm takes big O of v square plus v log v time. Therefore, Prim's algorithm runs somewhat faster than Kruskal algorithm. Now, let's talk about Steiner spanning tree. Now, Steiner spanning tree is a more practical spanning tree because we do not usually need to connect every vertex of the graph. We are just interested in connecting a specific subset of vertices, which are called terminal vertices, and these we want to connect them in the minimum weight possible. And as explained, to connect these terminal vertices, we need the help of some non-terminal vertices, which are called Steiner vertices. And that is why the name is called Steiner spanning tree. Now, in literature, there are large classes of Steiner spanning tree, but in this paper, we limit the scope to elementary Steiner spanning tree. Now, the formal definition of a Steiner spanning tree is that given a connected undirected graph G with vertices V and edges E, the weight of each edge is an integer, and the set of vertices N is known as terminals, whereas N is a subset of V. Then the problem is to find a Steiner subset of subset T, which is a subset of E, which spans all the terminals, and the total weight of T is minimum. Now the algorithm. The algorithm consists of two parts in which we propose. First is modified Prim's algorithm. So we modified the Prim's algorithm by which will be explained later. And also the second part is on the modified Prince algorithm, we construct a Steiner spanning tree. So what is Prince algorithm? In this, we run from a source vertex and run until all the vertices can be reached from the source vertex and with the minimum possible weight, right? And in the modified Prince algorithm which we propose, since we are interested in only connecting terminal vertices, so our algorithm, the iteration stops once all the terminal vertices are absorbed in the the tree. So that is why it is called there is a modified Prince algorithm. Now this is the pseudocode. So here we have the input as set of vertices, and E the set of edges, and T is a set of terminal vertices, and the output is a minimum spanning tree. Now, first step is once we sort all the edges in and by the order of weight, right? So minimum weight first and the maximum weight in the last, and then we extract one edge which has the minimum weight first, and then it has two vertices U and B, right? We add this two vertices with the minimum weight into the set A. So A set contains all these two vertices, and then we eliminate this edge from the big set E. And the set V, capital V, is the set which contains the difference of the all the vertices minus the vertex which we chose with the minimum weight, right? And in the main loop, we run it until all the vertices are become null, right? So all the vertices are absorbed, or we cover all the terminal vertices, right? So first we extract the edge with the vertex U and V with the minimum weight, such that the first U vertex is a part of set A, and V is a part of set V minus A, right? And then we add this vertex into our set A and delete this vertex from set capital V. And then we eliminate this edge from the capital E set. And we run this loop until all the terminal vertices are absorbed. And so the final set A is the set which contains all the vertices with the minimum weight, connecting all the terminal vertices along with some non-terminal vertices. So this is what the second step is, which is the modified Prim's algorithm. And then the third step, which deletes, so we want to delete the vertices which are non-terminal vertices, right? So for that, we delete all the non-terminal vertices with 1 degree of connection. And this step continues to delete non-terminal vertices and until there exist no more non-terminal vertices with 1 degree of connection. So here is the studio code for it. So again, we have set of vertices, E the set of edges, and T the set of terminal vertices. In step 1, we initialize the source vertex. In the step 2, we run our modified Prim's algorithm. And the result of modified Prim's algorithm is we get a minimum spanning tree, which connects all the terminal vertices along with some non-terminal vertices, right? And then here in step 3, we delete all the non-terminal vertices with 1 degree of connection. So this gives us our final minimum spanning tree, which is a Steiner spanning tree. To explain with an example, suppose this is a graph which has vertices, 9 vertices, and these red with the red circle, these are the terminal vertices which we want to connect in the minimum weight, right? So and these are the connections, so these are the weights, right? So I and J are connected with each other through, and the weight is 5. J and K are connected with each other with weight 6. So, and these are non-terminal vertices. So what are non-terminal vertices? J, P, Q, O, and L, right? And next step is we run our minimum spanning tree. right? Sorry. So we want to, we use, the first step is we use a modified Prim's algorithm. So when we run a modified Prim's algorithm, then we get this path. So we connect all the terminal vertices with non-terminal vertices. So what are the non-terminal vertices? What is the path which we found? So which is shown by these yellow lines. So we find the path which connects I, J, K, Q, N, M, L, O, and P, right? So all these are connected and we find these path, right? Next, we want to we want to do the step where we want to delete all the non-terminal vertex with 1 degree of connection. So 1 degree of connection, as you can see, what are the non-terminal vertex with 1 degree of connection? So you can see it is P and Q. Q is connected just with vertex K, and P is also connected with just with vertex O. So we delete these two, right? So in the resulting tree, we delete P and Q. So we end up with vertices I, J, K, N, M, L, and O, right? So this is our resulting spanning tree, which by deleting non-terminal vertices with 1 degree of connection. So as explained, since finding a minimum Steiner spanning tree is a NP-hard problem, so there does not exist a solution which solves the problem in polynomial time. And so we found out the runtime of our proposed algorithm as big O of V square. So step 1 takes O1 time, as it is the step which involves only simple assignment. Step 2, which is our modified Prim's algorithm, it takes O big O of E plus V log V, which is equivalent to O big O of V square for dense graphs. And the step 3, which deletes the non-terminal vertices that have 1 degree of connection, there will be a maximum of V minus N number of non-terminal vertices. And this step takes OV minus N time, right? So there is the running time of the total algorithm is O1 plus OV square plus OV minus N, which is equal to OV square. Now, this algorithm is implemented in a tool known as General Purpose Petri Net Simulator, GPenSim, which is developed by the second author of this paper, and GPenSim is freely available. And for the future work, we want to implement in an application which is a manufacturing system application and in smart grids. So to find the minimum possible way in which we can connect these terminals and find a possible solution in both these domains basically. Thank you so much for listening.